Okay, so today we are going to discuss linear transformations of vector spaces. Before going towards the linear transformations of vector spaces, I want to discuss a linear map. So what is a linear map? So a linear map, let me say if f is a linear map, if f of x is a linear map, and let me say f is a map from real numbers to real numbers. So what will be the properties which need to be satisfied by this function or map? So the first property which need to be satisfied for this map to be linear is called additivity. Okay, so what is additivity? Additivity of a linear map means f of x plus y is equal to f of x plus f of y, which means that if I perform the addition of the inputs first and then I apply the function, the result will be same, that I first apply f on each function and then sum the result. So f of x plus y is equal to f of x plus f of y. And the second map is homogeneity or scalar multiplicability, scalar multiplication. This one is the first property, and let me write this in red. So I delete this. The second property is this one, that f of cx is equal to c into f of x, where c is a scalar. So this is the second property. We can call this property homogeneity. Or simply scalar multiplication. So if a function satisfies these two properties, which is the first one is this, f of x plus y is equal to f of x plus f of y, and the second one is this, f of cx is c f of x, then we call such a map a linear map. What will be the examples of this? So let me say if we consider this map, f of x is equal to 3x. So this is a linear map. You can verify this. Let me say if I give this x plus y, so what will I obtain? 3 into x plus y, and this will become 3x plus 3y, and this is f of x plus f of y. So it means that this is a linear map. If I consider, for example, this function, f of x is equal to x square, let me check whether it is a linear map. So this means this is f of x plus f of y, and there is extra term. So it is non-linear. It is not linear map, or it is a non-linear map, because this is not equal to this is not equal to f of x plus f of y. Similarly, it fails this condition, so it is a necessary condition, additivity, so therefore it is a non-linear map. Let me check this map. Okay, so first I check the additivity property. What will happen? And you can see that this is not equal to f of x plus f of y. So this map is also not linear map. If we consider conjugation, so of complex number, conjugation of complex numbers over the field of real numbers. So let me say f is a function, and if I put z in this, so I will get complex conjugate of this. Z bar means complex conjugate. So is it a linear map? So let me verify. From z1 plus z2 will become z1 plus z2 whole conjugate, and this is actually z1 conjugate plus z2 conjugate. Now as the first property is satisfied, so I need to check the second property, and if cz1 is equal to c z1 conjugate, c belongs to the real number, so it becomes cz1, and this means this is equal to c f of z1. So it means that this is a linear map over the field of real numbers, but the same map is not real, is not linear over the field of complex numbers. So for example, so I can make the statement that the same f r conjugation is not linear over the field of complex numbers. So let me say if I take this function, the same function f of z, z bar. So let me say if I multiply c with z, so then it will become c z bar, and this is not equal to c f of z, where c belongs to the field of complex numbers. So these were some of the examples of linear maps, and we see that this linear map also depends upon the field from which you are taking the scalar numbers. Actually, these scalars belongs to a specific field, and sometime a map may be linear for one type of field, but it may not be linear for another type of field. We can see this from this example, that this conjugation map is actually linear over the field of real numbers. If C belongs to R, so then it is linear in that case. In this case it is linear, but in the case of complex numbers, the same is not linear. The same function is not linear. Okay, so after doing a general discussion on linear maps, now we shift towards the linear transformations. Linear transformations between vector spaces, and we assume finite dimensional vector spaces. You must be familiar what is meant by a vector space, finite dimensional vector space. So let T be transformation from vector space V to vector space W. The dimension of T, the dimension of V is n, and we assume that W has a different dimension, so that it is a general case. Dimension of W vector space is M, and T is a transformation from V vector space to W vector space. Now we say that, we claim that this T can be represented by a matrix. Then linear transformation T can be represented by a matrix. Okay, so what is the proof of this? Okay, so we know that T is we know the dimension of both vector spaces, and we know that T is actually a transformation from V to W. Let us take the basis of vector space V, BV. BV is actually the basis set of vector space V. So let me represent this V2, V1, V2 up to Vn. So these are actually the basis vectors. Vi is actually basis vector. And there will be also basis set for W vector space. So that will become BW. And I represent the basis vectors of W vector space with W1, W2 up to Wm, because the dimension of W is M. Now, as you know that any vector belonging to V can be represented as a linear combination of these basis vectors. We can represent any vector in vector space V as linear combination of these basis vectors, and similarly we can represent any vector in W vector space is a linear combination of these basis vectors. So let me take a vector V belonging to V vector space. So then I can safely write this V as C1 V1 plus C2 V2, and this summation will go up to Cn Vn. Okay, I can also write this V in other manners. One is that I can write the same vector V as a row vector, C1, C2 and C3 up to Cn. This is also a representation of the same vector, where I assume that C1 is actually coefficient coordinate or component of V1, C2 is the coordinate with V2, C3 is with V3 and Cn is with Vn. So I can safely write this V vector also in this form. This vector can be safely written also in this form. Okay. So similarly I can also write the same vector V also in this manner, C1 up to Cn. So this is the representation of the same vector in different manners. I call this a row vector. It's actually a row vector, and this one is column vector. This column vector is actually the transpose of the row vector. So now I know that if I apply transformation T on vector V, then this transformation will also act on the right hand side, C1 V1 plus C2 V2 and up to Cn Vn. So this will become Tv will become, because of linearity I can apply this transformation. I can take this C1 outside and T will go inside, and I can do this for all these terms of the summation. So what this will become, C1 TV1 C2 TV2, where I have used the linearity of this transformation. Now actually this TV belongs to W vector space, because after transformation this V will go into the W vector space. So what happens if I draw it graphically? So let me say this is V vector space, it has basis BV, and here we have W vector space and it has basis BW, and there is this transformation T, and if I take a vector V from here, then I will obtain TV over here. So actually this transformed vector lies in the W vector space. So once it is in the W vector space, then I can use the basis, because each vector in W vector space can be represented as a linear combination of the elements of BW, of this the basis of W vector space. So I can safely write TV as I can write this. We can also say it in this manner. For example, if I consider V1 here, which belongs to the basis element here, and I apply T on this, so it will be TV1, and this TV1 also belongs to W. So each of TVI can be written as a linear combination of the basis of the W vector space. So for example, if I consider TV1, So TV1 will become, actually this is the transformation on the basis vector V1. So this will become, let me say, A1 1W1 plus A1 2 W2 plus A1M WM. Because I can express this TV1 vector as a linear combination of the basis vectors of W vector space. In the same manner, I can write TV2 in this manner: A21 W1 A2M WM, and in similarly this will go further, and we have TVN to AN1 W1 plus AN2 W2 plus ANM WM. Okay, so I have this type of representation. Now, if I call this equation, let me call this equation 1. So here you can see that there is TV1 here, TV2 here, up to TVN, and now I have expressed each of these TVs in terms of the basis of the W vector space. So I can do that substitution over here. So TV, let me write it again for convenience. TV is actually C1 TV1 plus C2 TV2 CN TVN. Okay. You know that I can safely write this expression also in this manner: C1 C2 to Cn and TV1 TV2 to TVN. So we can write this expression also in this manner, and then this can be written here in this manner: CV1 C2 up to Cn, and now I substitute the values of these. So TV1 will become AN1 W1 and plus, okay, the first one is this one, so I delete this, A11 W1, and finally we have A1M WM, and then the second one is A21 W1 plus A2M WM, and then we have this AN1 W1 ANM WM. Okay, so these two expressions are actually equivalent. So now this means I can safely write this expression also in this manner. Okay, so we can write this also in this manner. This will become C1 A11 W1 plus A1M WM and plus C2. I can write it here. Delete this, so I can write it here as well, plus C2 A21 W1 and this goes up to A2M WM, and this summation will go to Cn AN1 W1 ANM WM. Now what I do is that I select all the terms which are with W1. I combine all those terms, and similarly I combine all those terms which are with W2. So this will become C1 A11 and similarly plus C2 A21 and similarly this will go up to Cn AN1. So all these terms are actually with W1, and similarly this summation will go to, what will come here? Now I come with terms which are with W2. So what will be with W2? C1 A12 plus C2 A22 and plus Cn A2 Cn. So this Cn is actually coming from here, and then this will become here it will become ANM. So let me not confuse it. So I am taking C11 A11 W1 and then C2 A21 from here, this is from here, and then this is from here. So the next term will all comes from here where there is W2. So what will come? C1 A12 C2 A22 and then Cn and A2 AN2 will come. Yes. AN2 W2, and this summation will go, and what will be there finally? I will have to take the terms which are with Wm. So what are with Wm? All these terms, the one here, the one which is over here, the one which is over here, the one which is over here. So this will become C1 A1M plus C2 A2M and finally Cn ANM WM will come. So this will become the final form of the TV. Now I can safely write this vector. You know that this is the same expression as this one, which I have over here. This one is here. So you know that there is C1 V1 plus C2 V2 plus Cn Vn, and then I can write this expression in this manner: C1 C2 C3 up to Cn. So the same situation is here, just the difference is that you can see that, let me highlight, that you have W1 over here, W2 over here, up to Wm. So these are the basis of the W vector space, and these are actually the coefficients. So in the row vector form, we can write this in this manner. You are familiar with this, that I can write this in the form of a row vector, and in the form of a row vector, this will become C1 A11 plus C2 A21, and this will go up to Cn An1. So this is the first element of that row vector. The second one is this one. So I will just write the first and the last term of this. So for W2, what will come? C1 A12 or plus up to Cn An2. And similarly, this row will go on, and the final term in this row will become this one: C1 A1m Cn Anm. Okay, so this is the vector TV, which actually belongs to the W vector space. Now I can write this also in this manner. C1, C2 go up to Cn, can verify this, and what will come here? A11 will come here, and then A12 will come here, and similarly A1 n will come, and here A21, 22 to A2n, and this will become okay. The final one is here. Actually, we have here A1m, so it will become A1m. Let me delete this. So this will become A1m, this will become A2m, and similarly the last one will be An1, and this will become Anm. So you can verify that this multiplication will give me the same thing, okay? Because you see C1 A11 plus C2 A21, once you do this multiplication, you obtain the above equation. Actually, these two are the same equations. So now this is actually the transformation matrix. This is T, capital T, and we call this T transformation matrix. So actually what is happening, that I have the transformation matrix. I can write this like this: transformation on vector V is given by the representation of this vector V, which is this C1, C2 up to Cn, and multiplied by this matrix T. We call this like this. This matrix T is the transformation matrix. So this is actually in the row vector form. I am taking everything in the row vector form. So TV will give me the coefficients, as I know that TV actually belongs to W vector space. So it will have some representation over there, and the components of this vector in the W vector space will be, if I represent this TV with the help of, let me say, the coordinates are D1, D2 up to Dm. So then what is happening, that this D1, D2 to Dm is given by TV, and this is equal to D1, D2, Dm, and this becomes equal to, let me put the mic. And this becomes equal to C1 to Cn multiplied by the transformation matrix. If I am interested in the column vector form of this, so then I can write it in this manner: D1, D2 to Dm is given by, for this I need to take the transform of both sides, transpose of both sides. So this will become transpose of this matrix and C1, C2 to Cn. So this is actually the way that we take these transformations. So this is actually the transformation matrix. If am I interested in the row vector form, then the transformation matrix will be in this form, and if I am interested in the column vector form, then the transformation vector will be in this form. So this means that I can take any linear transformation in the form of a matrix. Okay, now the question arises that how I can find the transformation matrix. Okay, so if I know that there is a transformation from V to W, from V vector space to W vector space, now how can I go and find the matrix for this transformation? So it is very obvious from here, you can check this, that this is actually the vector form. This is the row vector form of the some vector from the vector space V, and if I multiply it with this matrix, so I obtain the transformation. So it means actually I can obtain the transformation matrix by applying T at the basis vectors. You can see I have applied T on T V1, V2, Vn, where these basis vectors are in the row form. So I can obtain the transformation matrix in this manner. I just need to apply T on the basis vectors. In the column form, if I want to obtain the transformation matrix, so then the transformation matrix will become, T will become, I just need to apply T on the basis vector V1, T V2 and T Vn. So, I will obtain a matrix from this, and this matrix will be actually my transformation matrix. So, let me take some examples of these transformations, some simple examples. So, for example, if I have this coordinate system, so this is a two-dimensional vector space, 2D vector space, and here on the x-axis, this is the x-axis, this is the y-axis. So, this is actually the unit vector x cap, this is the unit vector y cap. So, if I represent this the basis vectors, so what are these basis vectors? X cap and y cap. Okay. And this basis set will become, I can call this x cap V1 and this V2. And what is this V1 actually? This V1 is actually 1 0 and V2 is 0 1. Can verify this, that this forms a basis set. Now, let me say I want to do the operation of rotation by 90 degree, rotation by 90 degree. So, let me say if there is a vector over here, if A is a vector over here, so once I rotate it by 90 degree, it will come here. Say this is 90 degree. So, this will be after transformation. So, how can I do this? I need to find 90 degree rotation. So, for that I need to take the transformation vector, and the method with me is in the column form. This is T on V1, T on V2. This is the general method from here. You know this general methodology is this one. So, this means this T will become okay. What this transformation does on 1 0? After 90 degree rotation, this will come here. So, it will become 0. So, if I apply transformation on 1 0, here is the transformation on 0 1. So, this will become, after transforming this 1 0, this will become 0 1 and 0 1 will become 1 0. So, this is the transformation matrix. You can verify this. If I apply this matrix T on, let me say, V1, so what I obtain? 0 1 1 0 1 0, I obtain 0 1. Okay, so when I give as input 1 0 vector, which is along x axis, and after application of transformation, it is rotated by 90 degree. Let me say if I give this vector A vector, and A vector is actually what? It is 1 1. So, the 1 1 vector will come here. This is actually in column form 1 1, because its x component is 1, y component is also 1. So, let me apply this transformation on this and see what happens. Okay. Actually, if I rotate this 0 1, so I will get minus 1 0. So, here this is minus 1. Remember, this is minus 1. So, for this it is all right. Now, if I apply this T on A, so what will come? 0 minus 1, 1 0, and if I apply on this on 1 1, so this from this I obtain minus 1 0. Okay, so this way minus 1 1. So where is this minus 1 1? It is here, because this is minus 1 and this is 1. So what has happened, this t vector has rotated this vector by 90 degree. Similarly, we can have scaling. Scaling is also a linear operation. Let me say if I want to scale a vector by some number, scale an object or vector along x-axis by k. So what will be the transformation matrix for this? So again, the transformation matrix has the general formula in case of 2 dimension, this. So if I scale along x-axis by k, so then k 0 will come, and tv2 I don't want to change anything over there, so 0. So let me say if k is 5, and so then, and I apply this t on v1, so what will happen? 5 0 0 1 will come, 1 0 will come, and this will become 5 0. So this vector is stretched along x-axis by 5. So these are some examples of the linear transformations. So in this lecture we studied the matrix representation of a linear transformation, and then we did some examples, and hopefully this will be helpful. So if you like this, please subscribe this channel.